Okay, let's do some more Fibonacci facts. So in the last video, I did three different proofs for showing how to sum up the Fibonacci numbers. And in this one, we'll sum just some of the Fibonacci numbers. So here's a nice little idea. Let's add up the odd Fibonacci numbers. So I'm going to call it O sub n is going to be the sum of the first n odd Fibonacci numbers. So again, I want n terms in my sum, and I'm going to add up f2i plus 1. Now, there's a couple ways we could go about this. I could tell you what the answer is, and then we could verify it. Or we can go right to trying to discover it ourselves by using something like the trick we had previously. So let's see. Can something like that work? Can we just telescope this in some direct way? Before, if you recall, with the other summations is that we rewrote this term that inside the summation using the definition. So remember, in the definition we had fn is equal to fn plus 2 minus fn plus 1. And one thing that is not so nice about that is it's not clear that when we're only doing the odd numbers, whether we'll get any kind of telescoping from this substitution. So if we want to get some telescoping, we're going to have to do something a little different. What can we do? Here's an idea. What if instead I wrote the following? Fn is also equal to fn plus 1 minus fn minus 1. It may take a moment to see that this is, again, the same recurrence, but now somehow I get a gap of 2, which might be useful for us because we're going only every other, so let's see if this works. So let's bring it down so I have room. So this would be equal to, again, the sum here. This will be f of 2i plus 2 minus f of 2i plus 1 minus 1, which is f2i. There we go. And I've written it this way, but actually, perhaps a more useful way to write this is to see that this, I'll erase it, and this one right here was really 2 times I plus 1. And this way, it's clear now that it's a telescoping sum because I have, for each index I, I'm looking at this mapping that goes from I to f to I. And so this is that mapping applied to I plus 1 minus I. So this whole thing will telescope to just be f to n minus f2 times 0, which is f0, which is just f to n. So there's this pretty surprising fact now, I'll write it all in one line so we can see it, which is that the sum of the first n odd Fibonacci numbers, so 2i plus 1, is just equal to f to n. Pretty neat. And we get it really directly from telescoping. We just had to use a different form of the recurrence. From this, we can actually also figure out pretty quickly what the sum of the first n even Fibonacci numbers would be. I'll give you a second. Can you think of how we might figure out this closed form for en, which would be, again, I'm going to sum n terms, but this time I just want even Fibonacci numbers, so f2i. All right, so the hint I would give is that we know what the sum of all the Fibonacci numbers are, So we can figure out what, and we know what the odd ones are, so the evens are just whatever is left. So if you recall, we know that, let me write it this way. We wrote this sum Gn, which was the sum of all the Fibonacci numbers. And if I was to sum up to, let's say, 2n, this would be G2n. And the first 2n numbers, n of them are odd and n of them are even. So this is just equal to O(n) plus E(n). But if you recall, we actually already have a closed form for this. We know that Gn(2n) would be F 2n plus 1 minus 1. And we have a closed form for On, so this would be F 2n plus En. And so putting these together, we get that En is equal to F 2n plus 1 minus 1 minus F 2n. You might be ready to see that sums of consecutive Fibonacci numbers gives you the next Fibonacci number. It's also the case that differences of consecutive Fibonacci numbers give you a Fibonacci number. And this is the technique we used for the recurrence before. So if I take F2n plus 1 and I subtract F2n, I'm going to get F2n minus 1, and the minus 1 remains. Okay, so to summarize these facts, we have the following. We have Gn, the sum of the first n Fibonacci numbers, is equal to Fn plus 1 minus 1. We have En, which is the sum of the first n even Fibonacci numbers, was equal to, oh, we didn't finish it. We left it in terms of 2n minus 1. Oh, that's right. So that's right. We want that. So that's F 2n minus 1 minus 1. And the sum of the first n odd Fibonacci numbers is this sum for I and n, F 2i plus 1. That's just equal to F 2n. Okay, so there we go. That's our some of our other ways of summing subsets of the Fibonacci numbers. Here is another cool Fibonacci fact. We can take the sum of the Fibonacci numbers, but we can also take the sum of their squares. So let's say that Sn is equal to the sum of the first n Fibonacci numbers, but I'm going to square each of them. Again, I could tell you what the answer is, and we can try to verify it by induction, but this is one where I think we can try to work it out ourselves. So the first thing to do is to just write out some values. So an empty sum will sum to 0. If I sum just the first Fibonacci number, which is 0, even squared, it's still 0, plus 1 squared is 1, plus the next Fibonacci is 1, so another 1 squared is going to be 2. And then maybe to help us remember what we're adding up here, let me write down what the Fibonacci numbers are. 1, 1, 2, 3, 5. And now I'm adding the squares here. So I want to add a 4 to this, I'm going to get 6. I'm going to add a 9 to this, I'm going to get 15. I'm going to add 25 to this, and I'm going to get 40. Actually, these numbers seem a little mysterious. It doesn't seem like there's immediately any kind of pattern here. Let's see what we can do with it. So we had some success in the past just plugging in the definition of the Fibonacci recurrence into these sums. And so we could try something like that. Like we can replace fi squared with something else. So let's try something like, well, fi is equal to fi plus 1 minus fi minus 1 times fi. Is that useful? I'm not sure. Let's see. When I do that, I think this is a good choice because when I distribute that through, I get fi plus 1 times fi minus fi times fi minus 1. And again, I'm looking for terms that have this symmetry where they look like the same term but shifted by 1, and I subtracted them. That's going to be the key to telescoping. So if I write it this way, in fact, I do get a nice telescoping sum, and so I'll see that Sn is equal to the sum of fi plus 1 fi minus fi minus 1, which, since it's a telescoping sum, I can just plug in the bounds, and what I get is n plus 1. No, I get fn, fn minus 1 minus f0 minus 1 is minus, we're in trouble, because what the heck is f minus 1? So somehow with my telescoping, I somehow got myself in trouble. But there's good news, because if I look at this sum, I didn't really need to start at 0, because if I start at 0, I'm just adding in a 0. So if I wanted to, I would not change anything if I instead sum from 1 to n. And in that case, the base case would be not 0, but 1. So this would be f1 times f0, which cancels out to 0. And the whole thing comes out to be just fn minus 1. So that's our theorem, or at least that's what we would like to prove. And we just derived it by the telescoping sum, and so you could do that yourself, or you could also, if you wanted to now, if someone said to you, hey, this is Sn is equal to fn times fn minus 1, and you were going to prove it by induction, you would write out the definition of Sn, which is right here. You would pull out the last term. You would apply induction, and then you would use take that last term, probably expand it in some way similar to this, and be able to rearrange the terms to get exactly this form. So this is the sum of the squares of the Fibonacci numbers. Now there's one more that I'm tempted to do, but it will seem a little more mysterious. So let's try it. Let's see if I can get it right. So I'm going to call this Tn. And instead of summing the squares, I'm going to sum the products of consecutive terms. So this is something like the following. It's the sum of the first n elements, or indices here, but I'm going to take fi plus 1 times fi. Now, we know what this is, that this itself is the sum of squares, because that's what we just derived. But I don't think that's going to help us immediately. So I want to figure out what this is. So first I'm going to try to write out some values of it. And I'm going to do it in 3 steps because I find that way easier. Let me put them over here. So first I'm going to write the Fibonacci numbers. And then I'm going to write the products of adjacent ones. So this will be just the terms inside the sum. So this will be 0, 1, right, I'm taking the product for each one. So this is 2, this will be 6, this is 15, 40. Wait a minute. I recognize this. Do you recognize this? We should recognize it because, of course, we know what these terms are. This is exactly the sum of the squares. This is the sequence we just did. But this is not the sequence we were looking for. We're looking for the sum of these things. So the next one, 8 times 13, what, 60? Is that... 8 times 13 is 80 plus 24, 104. That looks good. And I'm not going to keep going. That's good enough for now. So these are the consecutive ones, and now we're taking the sums of these. So the empty sum is 0, the sum of just the first one is 0, the sum of the first two is 1, and 3, 9, plus the 15 gives me 24, plus the 40 gives me 64. As I look at this, there's something, maybe there's a pattern you see, is that it looks like I go one, like I square, if I go down, I see these squares for every other one. But then every other one is like the square minus 1, right? 2 squared minus 1 is 3. 1 squared minus 1 is 0. 0 squared is 0. So it seems like there's a difference between the odd and the even terms. And that's a little strange. And I'm not sure if we can immediately see why that's the case, but we're going to eventually see why that's the case. So we could, if from here, we could write a conjecture, which would be maybe in 2 parts, which is that if n is even, then this is fn squared. And if n is odd, it seems to be fn squared minus 1. Okay, so that means that we could try to do this in 2 parts. And eventually we could put this all together into one step, but since we seem to have this alternating behavior, we can go ahead and try to do it separately. So let's start with the first conjecture that we're trying to prove, which is that if n is even, and I think, did I get even right? Let's see, let me make sure I got that right. So yeah, for term 0, term 2, term 4, right? So the indices here are 0, 1, 2, 3, 4, 5, 6, etc. Yeah, so it seems that for the even terms, we're just squaring the Fibonacci number. Then Sn, which is equal to the sum of these product of consecutive Fibonacci numbers, is just equal to fn squared. If I try to prove this using induction, let's try it. We do see that the base is pretty easy, right? So the base case, S0 is definitely equal to 0 because it's an empty sum, and that is the same as f0 squared. Now, by induction, we'll assume that this identity holds for all values less than n, and we'll try to prove it's true for n. And so the usual trick would be to try to pull off the largest term, which would be something like this, and then apply induction somehow. But we are in a bit of trouble because the theorem, or the conjecture at this point, is only true for even values of n. So when I take an even value of n and I subtract 1, it's odd. So I won't be able to replace this with something. So one way to get it to be even is to do it again. So I'm going to do 2 steps at a time. So now I'm going to go I to n minus 2 of, again, the same terms, I plus 1 fi, and now I've got 2 of these terms. I've got the one I had before, and I've got the next one. Okay, now this is now Sn minus 2, and so we could write this now as f n minus 2 squared plus fn minus 1 plus fn minus 1 fn minus 2. Whew. All right, now there is a fair amount of algebra that we can now do, and the hope is that when we do it, we will end up with something that looks like fn squared. I think the easiest way to do this, though, is just to derive that the difference between fn squared and fn minus 2 squared is just equal to this. And so let's check that. So that's fn squared minus fn minus 2 squared. And this is a difference of squares, so we know how to do that. That's fn minus 2 times fn times plus fn minus 2. Okay, and this term right here, the difference of Fibonacci numbers, is just fn minus 1 times fn plus fn minus 2. And this, you'll see, is equal to this right here. Okay, so that's how we would derive it. It takes a little bit of work. But the key idea was that since we were only looking at the even numbers, we had to go 2 steps at a time. But after we do it, after we do this proof, we might notice something that's, I think, useful, which is that this statement, this last part of the proof, it didn't really matter that n was even at this point. Right, so this algebra that I did in red at the bottom, right, that's true if n is even or if n is odd. So it seems like at first, like we should have been able to apply this same technique either for n even or for n odd. But the difference is like what we'll get when we apply the induction hypothesis. Let's try this again. But this time we're going to just take Sn for n being odd or even. We're not going to specify too much. So we're just going to say, hey, I take Sn, it's the sum of n values of this fi plus 1 times fi. And I'm going to use this fact that we worked out, which was that f n plus 2 squared minus fn squared is equal to, what did we say it was equal to? We got, well, we did it for minus 2, but it was equal to a pair of terms that looked like this. It was f well, I'll just do it out. Fn plus 2 minus Fn times Fn plus 2 plus Fn, which after we replace this with Fn plus 1 and distribute it through, that's just going to be equal to Fn plus 2, Fn plus 1 minus, so plus rather, Fn plus 1 times Fn. Okay, so what we see is that if I were to take two consecutive terms of this sum, I would get something that looks maybe more like something that would telescope. And so let's do that. This is now Sn is then equal to, I want to sum these two at a time. So instead of taking all the terms, I'm going to do them two at a time. And I would like to just have an even number of terms. That would be ideal. But the good news is if I don't have an even number of terms, if I have an odd number of terms, then I can just start at 1 because the 0th term is empty. So I throw out one of the terms, it's 0 anyway, and I'll get back to an even number of terms. That way I can break it in half and sum over something else instead. So what I'll get is the sum for j in, this is going to be, it's going to start at either 0 or 1, depending on whether it's odd or even. So I'll write it as n mod 2, and it's going to go up to the floor of n over 2. So this will have n over 2 terms, and when I add them all up, what are they going to look like? Well, they're going to look like f 2j plus 1 f 2j plus the next term as well. So I'm doing them two at a time. So this is f 2j plus 3 f 2j plus 2. That doesn't look right. Let's be a little more careful here. This should have been the next term, so this should have been 2j plus 2, 2j plus 1, which was equal to the sum now of just f 2j plus 2 squared minus f 2j squared. And this, as we saw previously, this is really like saying 2 times j plus 1. And so this will telescope as well. And what we should get is just plugging in the last value, which was n over 2, will give us f 2 times n over 2 is just n squared minus the base case is 0 or 1, right? So in the case where it's 1, I'll get f 2 squared. So that's equal to fn squared minus 1. All right, so this doesn't look quite right to me. I think I've gotten off by one error in there, but I'm going to let you find it. We did get the theorem we wanted. I'm sorry, I wrote 1 here, but I meant, let's get this right. This depends on whether we're odd or even. So this is supposed to be 2 times n mod 2. Let's get that right. And so this is equal to, depending on whether it's odd or even, it's equal to fn squared if n is even. And it'll be fn squared minus, well, 1 squared is just 1. So it's minus 1 if n is odd. All right, so that's a quite trickier sum. And if you followed that, good for you. It was not easy. There's basically no end to the fun Fibonacci sequences or Fibonacci identities that you can prove. I will leave you with one that I think is quite wonderful, and you tell me if you find a nice solution. So my claim is that if I define the following sequence, it's hn is going to be hn minus 1 plus hn minus 2. You say, I know this one, that's Fibonacci already. Almost, because h1 is going to be 1. There's going to be no h0 actually at all. Or if you like, you could start at h0 equals 2, but I'll do it this way. And h2 is equal to 3. So given this sequence, I claim that hn is equal to the quotient of f2n divided by fn. This is one I just sort of stumbled upon while I was trying to come up with an interesting homework question. Hopefully you'll have some fun trying to prove it.